So I will continue talking today about period doubling cascade and Feigenbaum constants. Now, what is period doubling cascade? So this is our parameter R for logistic map. Probably I will write it again. Un plus 1 equals R un 1 minus un. It's what we consider. For now, R is between 0 and 4, and u naught is in the domain from 0 to 1. So for example, here R is 2, we have U2, which is stable, then it becomes unstable at R equal to 3, we will call it R1. So here it becomes unstable, this is of course our U2 fixed point, and two-periodic solution appears. Then two-periodic solution, when it appears, it's stable, but when it becomes unstable, at some value R2, we know this, what this R2 is 1 plus square root of 6, and then they become unstable, and four periodic solutions appear. Then these four periodic solutions become unstable at some point, and 8 periodic solutions appear, and so on. So what we will have at some point, we will have R infinity when here infinite periodicity appears. Infinite periodicity. So this is say R3, then somewhere here will be Rn, and so on. So first Feigenbaum constant was about limit of this ratio Rn minus 1 divided by Rn plus 1 minus Rn, and this tends to first Feigenbaum constant, which is roughly 4.67. So what it says, it's basically about ratio of these segments, this segment and following segment, then following segment. So every next bifurcation appears sooner and sooner. So this is first Feigenbaum constant we estimated. R infinity, and this was roughly equal to 3.54. So here we will. On the other hand, there is another Feigenbaum constant, and this is associated with scaling along U. Scaling along U axis. So what it means? Let's consider this distance. This is distance between U3 and U4 at the time when U3 and U4 become unstable. And this is another distance between, let's say, U5 and U6. It's again distance between fixed points U5 and U6 in certain map. When they become unstable, or let's put it like this. So distance between U3 and U4, it is a distance, this distance, when period 2 solution U3, U4 becomes unstable, and this distance roughly equals to this distance. It is a distance between U4, U5 and U6, U7 when 4-periodic solution becomes unstable. And we can look and we can find other distances, and we see that these distances get shorter and shorter. And for these distances, we also have, so we will denote like this. This distance will be delta U1, this will be delta U2, this will be delta U3, and so on. And then what we can say delta un minus 1 divided by delta un, it is scaling in this along the period doubling cascade. This also tends to some constant, which is denoted by alpha, and roughly equal to 2.50. And this is second Feigenbaum constant. Okay, so we have two Feigenbaum constants, and they called universal constants. Universal. Why are they called universal? If so, many maps, in many maps we can see period doubling cascade can appear in many maps. Can occur in many maps. And Feigenbaum constants have same values for all maps. So this is why they called universal constants. Whenever we see period doubling cascade in whatever map, then we can definitely state that there are two scaling constants, scaling along parameter and scaling along our variable, and these two scalings are given by first and second Feigenbaum constants. Both constants eventually can be derived from, so according to a certain theory. Derivation of first Feigenbaum constant is quite sophisticated, but I can show how to estimate at least second Feigenbaum constant. So I will use these plots for derivation or for illustration how I want to estimate second Feigenbaum constant. So estimation of second Feigenbaum constant. So here we have our function f of u, which is logistic, which generates logistic map, and here r equals to 2. So this is our logistic map. So basically I can put it like this: f of u is 2 times u times 1 minus u. So this fixed point u2, we remember it is superstable. Now this is two composite map, which is f of u. And here we will take value of r, which is, well, it should be equal to 1 plus square root of 5. And for this value of of R. So here now this is U2, this is U3, and this is U4. So at this value of R, U3 is super stable. Now let's plot here a square. So square here, it starts at U2. This is diagonal, this is horizontal line. Here we have two vertical lines. And this should be square. In this square, what is important, this should be equal to this, because this and these points lie on diagonal line. This should be equal also to this, because this is symmetric. This point and this point symmetric with respect to middle line, where our u equals to half. And we just extend it down to the same distance. This equals to this, equals to this, equals to this. Therefore, we will have a square. So now if we stretch this square, we will get this kind of pattern. So it's exactly what is inside of this square. And if we compare this plot with this, we see that they are similar. One can be obtained from the other after rotation. Well, 180 degrees. Yeah, so it's more or less evident what we get here. And now what I want to do, I want to represent this observation mathematically. So first observation is we have f of u, which generates our map, and we know that derivative of f when u equals to half equals to 0. Yeah, so it was a maximum in our logistic map. Then what we can say, if we consider second iterate, and if we take derivative of this when u equals to half, it will be also 0, because it's again symmetric and there is an extreme point. So here we have f of u, f when u is half is maximum, and here it's 0, f second iterate when u equals to half is minimum. And now so to take into account, to take advantage of this, we introduce new variable x, which will be equal to u minus half. And now if we make this substitution, then f of x, derivative of f of x, when x is 0, will be 0, and also derivative of second iterate of x, when again x is 0, also 0. And furthermore, we can note that f when x is 0 equals to half, and second iterate when x is 0 is also equal to half. It is because we have super stable fixed point in both cases, as we see in here. This is super stable, and this is super stable, so this is half and this is half. And therefore what we see that we are rotating, so in order to get f of x, so we are rotating along line here half and here half. So that's exactly middle of this square, which is 1 by 1 square. and also this square, which is much smaller, like so let's say if this, we'll call it epsilon, it will be epsilon by epsilon square. Good. In terms of x, we can put some correspondence between f2, second iterate of f, and f. So what it says, f of alpha x equals to minus alpha second iterate of f at minus x. Now what it means, this alpha, so stretching is by alpha, so alpha shows how much we should stretch this small square to get 1 by 1 matrix. So here epsilon would be 1 over alpha. And so since we stretch both along x-axis and along y-axis, we need to multiply by alpha our function and stretch here our argument x. And rotation, so it's again when we rotate this, we see that our x-axis changes direction and y-axis, both horizontal and vertical axis change direction, and it is given by here. So here change of horizontal axis, this minus takes into account, and this minus takes into account change of direction of vertical axis. We will solve this equation using its second order approximation, using Taylor expansion and second order approximation. What it means. So let's consider our function f of x first. F of x, so x is small number around 0. We remember that x equal to 0 corresponds to u equals to half. This can be represented as f at 0 plus f prime at 0 times x plus 1 over 2 second derivative at 0 times x squared. And since f, so f at 0, we can, let's call it b, some parameter b. So it is positive because f at 0, remember it is half. We could even put half. So this is 0, so the second term disappears, and this we will denote by c, so minus c, because second derivative is negative for function f. You remember it has maximum at 0. So if it has maximum at 0, then second derivative of function should be negative. So we will have b minus c x squared. So this is our f of x. Now, if f of x can be represented like this, f of alpha x, we can put it like this. So this will be b minus c times alpha x squared, or b minus c alpha squared x squared. And next point is to find second order approximation for two composite map with argument minus x. So f second composite function is f of minus x. F of minus x will be, so f of x is this. So here we will replace x by minus x. It will be b minus c times minus x squared, which is the same eventually. And so this is f of this. And now f of this, okay, f of b minus c x squared. And now we will put this expression into there instead of x squared. Yeah, it will be b minus c times b minus cx squared, which is after opening this bracket, we will have b minus cb squared plus 2bc squared x squared minus c cubed x to the power of 4. And this can be ignored. This is fourth order term is ignored. So what we have now, f2 of minus x, now we can put it here. So f2 of minus x, we found second order approximation, f of alpha x we also found second order approximation. Now this should be equal to minus this. So what we get is b minus c times alpha x squared should be equal to minus alpha times b minus cb squared plus 2bc squared x squared. And when we collect three terms, we get three terms which don't contain x. We will get b equals to alpha b cb minus 1. And from here we find expression for c. So b cancels, b and b disappears. C will be alpha plus 1. Here it's minus. Alpha plus 1 over alpha b. And collecting terms which have x squared, we get minus c alpha squared. So this is. And here it will be minus 2 alpha b c squared. And from here we see that c should be equal to alpha over 2b. And this and this, it's same c, they should be equal to each other. And therefore we get alpha plus 1 over alpha b should be equal to alpha times 2b, alpha divided by 2b. From these two expressions, we get equation for alpha, which is alpha squared minus 2 alpha minus 2 equal to 0. From here we can find alphas, roots alpha 1, 2 equal to 1 plus minus square root of 1 plus 2, or 1 plus minus square root of 3, and positive alpha, positive root. Alpha is 1 plus square root of 3, which is roughly 2.73. And this is approximation. This is an approximation to second Feigenbaum constant, which was, as you remember, 2.50 around. So it's very close approximation.